So today we will use the sigma notation developed last time to start to develop an integral. And so the whole theory of integration, just like there's this big theory of derivatives, there's also a whole theory of integration. And just like the derivative starts, we motivate it with a geometry problem. So as you remember, the derivative is motivated by the question, what's the slope of a curve at any point in its domain? And so then we start to answer that question and we get the derivative out of that. Here, the integral is also motivated by a geometry question. So the question here is, what is the area of the region, given some positive function f of x or x between a and b, what is the area of the region below the curve, above the x-axis, and between the numbers a and b? So this region here below the curve, this area, we want to answer the question, what's the area? And of course, here we're using it to find the area, but in applications, it may not just be area. It may be something more significant when we actually apply it to a real world application. So the way we develop the integral is it's in a two-step process. First, we ask the question, how can we approximate the area below the function above the x-axis between a and b? So first, we just want to start, essentially baby steps. Rather than find the exact area right away, first let's figure out how to approximate it. And then using that approximation, let's improve the approximation until the approximation is no longer an approximation, but becomes the exact area. So it's kind of a two-step process where we're building up to the final product, which will be an integral. So the procedure of constructing an integral is always the same. And in Calc 3, you will construct many different kinds of integrals. We're starting out with a very straightforward integral, but in Calc 3, you'll see that there are double integrals, triple integrals, and surface integrals, and line integrals. There are many different kinds of integrals, but the procedure usually starts out the same way. So we start by partitioning the domain, partitioning or dividing the domain. So for example, just for a toy example, suppose I divide this domain into 3 pieces. Ideally, they don't have to be equal width, but the way we do it in this textbook, we will use what are called subintervals of equal width. So first, we divide the domain into pieces, n pieces, where n is some positive integer. So here I've done 3 pieces. Then we approximate the area in these 3 pieces using a rectangle somehow. So for example, here I could use this rectangle here to approximate the area for that first one, for that first section. I could use a rectangle like this to approximate that second section. Actually, let me use a slightly different color. So I could use a rectangle like this to approximate that second section. And then finally, for example, I could use a rectangle like this to approximate the area under the third section. So exactly how we choose the rectangle, there will be some discussion there. We have some options and some freedom there. But at the end of the day, no matter how we choose the rectangle, what we will do is approximate the area under the curve in that section with a rectangle. Finally, we will find the exact area by doing the same procedure, except we will use rectangles that are super thin. Their width will literally be the width of a point on the x-axis. And so we will end up using infinitely many super thin, very, very, not wide, very thin rectangles, and we will get infinitely many of them. We'll fit infinitely many rectangles under the curve. And anytime infinity is involved, we'll have to do that with limits. So we'll actually, from approximation, using n rectangles, 3, 5, 10, 1,000, we'll make the approximation exact by using infinitely many rectangles. And the way we do the infinity part is with a limit. And I'll show you this whole procedure. I really want to lay out the concept first. At the end of the day, the concept isn't too difficult, nor is the math, but what's really irritating is the notation. And that's part of what we're here to learn today, is to learn the notation. The concept is not hard. And in science, that's part of science, learning and understanding the notation. Complicated topics sometimes require complicated notation, but that's okay. Our job is to learn how to learn notation. So in step 3, if the limit that represents the exact area actually exists, we will call that thing an integral. And we'll discuss the limits and all of this in great detail. I just wanted to lay out the big picture, which is partition the domain, find rectangles to approximate the area, and then, use infinitely many rectangles to find the exact area. These are all themes that we'll see over and over again. So let me talk about the partitioning process. So I say, ironically, we begin the process of integration by first partitioning. What do I mean by ironically? Think about what the word integration means. Integration typically means to put things together. Whereas here, partitioning is the opposite. We're dividing. And so it starts by dividing the domain. So here our domain is the interval, on the left-hand side, I have A to B. Okay, my domain is A to B. And here what we've done is we've divided the domain into n pieces. So for example, this subinterval here from x sub 0 to x1, that's our first piece. This second subinterval here, that's our second piece, so on and so forth. This last piece is our nth piece, where n could be 3 or 5 or 1,000. N would be a positive integer. And so we introduce some notation to, express the partition. So these numbers here, x sub 1, x sub 2, all the way to x sub n, they form the partition. They are the numbers that divide up the subinterval. Remember, x by itself typically is a variable, but x with a subscript is going to be a constant. And here, let me do a very quick, easy example. So suppose I had the interval is 0, 1, and I want a partition with 2 subintervals. Then I'm going to pick this middle point. I'm going to divide this exactly in half. 0 here will be called x sub 0. 1/2 would be x sub 1. And 1 here would be x sub 2. And I wanted a partition with 2 subintervals, and this ends with 2. That's not a coincidence. The way the numbering system is set up is this last term is always the nth number in our partition. So that's how we find a partition. We just divide AB into n equal subintervals. And so, we introduce this notation. Here's the first subinterval. Here's the second subinterval, so on and so forth. And, this is the part where the mind starts to get a little, oh, there's a lot of notation. What's going on? This is the part where you have to slow down and just go, it's just notation. What's the concept here? It's just notation. So if you look at all these subintervals, they kind of have a similar pattern. They're x sub some number, comma, x sub the next number. So we write it generically this way. This is an easier way to express all of the subintervals. So here, we can replace I with any one of these choices to find the ith subinterval. So for example, if you plug in an I equal to 1, in these two places, we get x sub 1 minus 1 would be 0, comma, x sub 1. We get back exactly the first subinterval. If I plug in I equal to 2, for example, then I have x sub 2 minus 1, or x sub 1, comma, x sub 2. That gives me exactly this second subinterval. So writing this more generic form, it's kind of a more generic way. It's a little easier to remember what a particular subinterval might look like. So here's the generic ith subinterval, whereby plugging in values of I, you can figure out exactly what the ith subinterval looks like. And this generic ith subinterval also allows us to identify the endpoints. So this I'm going to call the left endpoint. And here we have the right endpoint. And in particular, it's this notation that I'm keying in on, that the left endpoint we typically designate as x sub I minus 1, and the right endpoint we generically designate as x sub I. And having this generic diagram helps to see that this is the left side and this is the right side. I'll mention that again, it'll come up in a second. So here we use subintervals of equal width. That is to say, here the width of each of these is identical from x sub 0 to x1, x1 to x2. They're all exactly the same width, x sub n minus 1 to x sub n. In general, it's for the theory, it's not necessary. They don't have to all be the same, but that's what we'll do in this class, in this textbook. So now the actual approximation process. The thing to remember here is we're not doing anything more than multiplying and adding. That's what's really special about this procedure, that this procedure of integration is something we can do in a computer. We're calculating the integral numerically. Okay, that's known as quadrature, and I'll mention that again here in 1 second. So here, one way we can approximate the area is to use the right endpoints of each subinterval. So take a look at the generic ith subinterval here. And what we want to do is to use the right endpoint. So for example, in this first subinterval here, I want to use x1 as my right endpoint. So what does that mean? I'm going to approximate the height as f of x1. And so then I create an approximating triangle that looks, rectangle that looks like this, where the height is determined by the y value at the right endpoint. Then I move to the second subinterval. So for the first subinterval, my area would be f of x1 times delta x. So for my first subinterval, my area here is f of x1 times delta x. And now, we just do the same procedure all over again. I go to the second subinterval. So let me go to the second subinterval here. I look at the right endpoint. So here I'm looking at x sub 2, and then I find the y value at that right endpoint, and I'm going to use that as the height of my rectangle, and I can create the rectangle. And then I do height times width to get the area of that second rectangle. We do this procedure for every subinterval. So at the very end, I'm going to the last subinterval, which in this particular case, I used a partition with only 3 subintervals because that makes it easier to draw and visualize, okay? So I go to this last subinterval here. I'm gonna use the right endpoint, which tells me, now I use the y value at the right endpoint. And so now I can build the rectangle, calculate the area. The area is height times width, add them all. So it's really important. The procedure is very simple, but it's very important that you kind of match the notation. And one thing I'm going to ask you to do, and I'm going to bug you about, is when you read this formula, don't just read it as a formula. You have to see the story of this formula and tell yourself the story. What's the story? Well, we're f of x1, that's the height times the width gives me the area of the first rectangle. And now I'm going to add it to the area of the next rectangle, and we start the whole procedure over again, which is height times width gives me area. It's really important, otherwise it just becomes meaningless. And so one thing we notice is that all the formulas for the area look identical. It's the same formula. The only place where they're different is in the subscript. So we can write this using sigma notation in a very compact form. I can write this as sigma I going from 1 to n f of x sub I times delta x. So now what I immediately want you to do is practice reading the sigma notation. Start with the inside here. And even when you look at the inside here, I want you to tell the story. That's the height times the width of, so I get the area of the ith rectangle. And now I'm gonna add up the areas for all n rectangles. That'll give me my approximation. And of course, let's practice the notation. So when I see this notation, I'm thinking, aha, there's a sigma here. So this is a sum. It's a sum that's gonna start at 1 and end at n. And what am I summing? I'm summing this expression. So I start when when I is 1, I plug that into here, and that gives me this expression here, f of x sub 1 times delta x. Then I automatically slap down the plus symbol, because that's what the sigma notation tells me to do, is to automatically write down a plus symbol, because this is, repeated addition. Then I move to the next number. I say I equal to 2. So when I equals 2, I plug in. That gives me this expression here. So this is I equals 2. So on and so forth. And here I'm ending when I equals n. Again, plug in I equal to n here. That spits out f of x of n times delta x. What we should be seeing there is height times width. That's an area of the nth subrectangle. When we use right endpoints to do this approximation, the book uses the notation r sub n. So this is to indicate that we used the right endpoints, that's the r, and that we used n rectangles. So if I did, so here, this approximation that I've pictured here, technically this would be R3. Because I'm using a subinterval, 3 subintervals and right endpoints. So by the way, when we use numerical methods to calculate the area like we're doing here, as opposed to analytical methods, so in a second, I'll show you next week that we can use antiderivatives to also solve this problem. When we find the area using this type of formula, using height, the height times width, using numerics, this is called quadrature. Quadrature is more realistic in terms of finding an integral, because in the real world, we don't necessarily know, it's not necessarily easy to find the antiderivative of a function. In fact, not all functions have antiderivatives. For example, we're still trying to figure out what the antiderivative of 1 over x is. So in the real world, it's more practical to use a formula like this. This is something I can program in a computer, and this is something, our computers are very powerful now. We can easily calculate these types of calculations using very large n, like n is 10,000 or 100,000. We can do it fairly quickly because our computers are fast. So the quadrature here is, let's see this. Yeah, quadrature is when we numerically calculate the area under an integral instead of using an antiderivative, which is what we will do later in section 4.3. Okay, so quadrature is actually more practical from a scientific point of view. You're probably going to do quadrature more than you would finding an antiderivative. That's just not practical. It's a nice theory, but it's not practical. So as I said, there's many ways to determine the height of the rectangle. In the previous slide, we used the right endpoints, but there's no need, there's no fixed rule. We could have also used the left endpoints. So specifically here, if you look, This is a generic ith subinterval. And now what I'm doing is I'm choosing the left endpoint, the y value at the left endpoint. So exactly what does that look like? So if we go to this first generic ith subinterval right here, here's my first subinterval. Now I'm going to choose the left endpoint, the y value at the left endpoint for my height. And so now I can formulate my rectangle and now do width times height to calculate the area. Then I move to the second subinterval, which is x1 to x2. Same thing, choose the left endpoint, choose the y value at the left endpoint to be the height of the rectangle, and then we can formulate the rectangle. Then it's, height times width for the area. And then finally here, I'm sure you get the hang of this, I go to the third subinterval, pick the left endpoint, because that's what we've decided to do here. Use the y value at the left endpoint as the height of the rectangle, and then make the rectangle, and then do width, height times width. And so that's basically what I've specified here. The width is delta x. We assume the height is f of x minus 1. So look at that. X minus 1 is the left endpoint. And so f of xi minus 1, we're literally finding the y value at the left endpoint. That's literally what this is saying. And that's these points here that we used as the height. And then we can calculate the area. So here, look, this is different. On the previous slide, we had f of x1 times delta x. Here I have f of x sub 0 times delta x, because I'm using the left endpoint and the y value at the left endpoint, for the height here of this rectangle, right? And so you should tell yourself the story. That's the most important thing I can, that I can say here in terms of understanding it. Here, you should not just see some symbols. Here, what you should say is, here's the height of the rectangle where we're using the y value at the left endpoint times the width of the rectangle. So that gives me the area of the first sub-rectangle. So if I want to call this A sub 1, the area of the first sub-rectangle, that's fine. That's the area of this first rectangle. And then repeat the procedure. Add it to height times width. This is the height of the second rectangle where we're using the left endpoint. And we just follow this procedure all the way to the end. And once you do the sum, that's our approximation. And again, here we notice the formula, the actual formula is very similar from term to term. The only thing that's changing is the subscript. So we can write it in sigma notation this way. If you compare this formula with the formula on the previous slide, the only difference would be down here. When we use right endpoints, instead of x sub I minus 1, we have x sub I. But when we use left endpoints, what I have here is f of x sub I, which is literally the y value at the left endpoint. It's literally, it's the math way of saying use the y value at the left endpoint for your height. And so again, when you look at the sigma notation, see the story. Start within here, height times width is area of the ith subrectangle. Now let's add up the area of all n subrectangles. That'll give us our approximation. When we use the left endpoint, the book refers to this quadrature as L sub n. Capital L for left, because we're using the left endpoints, and the little n indicates how many rectangles we're using. So in this case, this example here that I've drawn, this would be, here this is L3, because we're using 3 rectangles and left endpoints to do our quadrature, to approximate the area under the integral numerically. And the final option that we like to look at in this textbook, we look at left endpoint, right endpoint, and then finally we look at the midpoint, the point right in the middle, okay? And so here's the midpoint. The midpoint formula is very simple. The midpoint is just the average of the endpoints. The midpoint is just right here. The left endpoint, the midpoint is just the left endpoint x sub I minus 1 plus the right endpoint x sub I divided by 2. That gives you the average of the two numbers, which is exactly the midpoint. So now the book thinks perhaps that this will help. The book introduces more notation. I don't know if this is helpful or not, but that's what the book does. And so let me talk about it because you'll see this in the book. So the book decides maybe writing x sub I minus 1 plus x sub I over 2, writing this over and over again may not be fun. So instead of writing this over and over again, the book introduces new notation and calls the midpoint x sub I bar. So please don't be confused. The x sub I bar is really superfluous and unnecessary. Really, we should really think about the midpoint in terms of the original partitioning variables, x sub I minus 1 and x sub I. This x sub I bar, it's actually a function. So here, it would be more appropriate to write x sub I bar. This is a function of x sub I minus 1, the left endpoint, and x sub I. I'm using function notation where I'm treating these as the inputs. So before I can find the midpoint, I need to know the endpoints. I need to know the left point and the right point. And once I know that, I can do the formula. And so rather than writing out this formula, the book is just calling the formula x sub I bar, which I'm not a real big fan of, but there it is. I'm not a fan of it because it introduces more notation and is potentially more confusing. So what we're doing, as you know, is now we're going to, for example, the first subrectangle, first subinterval, and I'm choosing the y value at the midpoint, which is right here, to be the height. And then I'm creating the rectangle using the y value at the midpoint as the height. And then we're doing our usual height times width. It's important you see that here. We're doing height times width, and we're finding the area of this first subrectangle. And then we just do this procedure again and again until we're done, So now I'm going to go to the second subrectangle. I'm going to use the height at the midpoint, to be the height of my rectangle. I'm going to create the rectangle. I'm going to do height times width. And then I go all the way to the end. And again, here we notice the formula is very repetitive. It's the same set of symbols, except the only thing that's changing is the subscript. So we can write it in sigma notation in a more compact form this way. And again, you should tell yourself the story. This is the height of the rectangle times the width of the rectangle gives me the area of the ith subrectangle. And then finally, I add up all n of the subrectangles to give me the approximation of the area. And like I said, I personally, I'm not that, I don't necessarily use the x sub I bar notation that much. So in terms of the original variables, this is really what it looks like. The book, for some reason, thinks it's nicer to replace this part with a new variable called x sub I bar. I don't know if that's helpful. I don't know if that makes it better or worse, but just so you understand what's going on. Really, at the end of the day, it's really just the left endpoint plus the right endpoint divided by 2. And so the quadrature using the mid endpoint and n subrectangles is called m sub n. Capital M for midpoint because we're using the midpoints, the y value at the midpoints for the height, and little n there says how many rectangles we're using. So here Here, what I have pictured here would be M3. The quadrature here to do the approximation of the area under the integral would be known as M3 here. So that's basically the whole story of how you find an approximate integral, approximate the area under the curve. And so we can use the approximation to find the exact area. So let me just talk about the theory of that, and then let me start showing you some nitty-gritty formulas for how you actually do some of this stuff. And like I said, remember, there's nothing other than multiplication and addition involved, okay? So in general, we can use this generic formula. And be careful now, the book has introduced even more new notation. This f of x of I star is not a typo. So let me talk about that. So if you look at all the previous formulas, they all have exactly the same form. They're all f of something. They're all f of something, either x sub I if I'm using right endpoints, x sub I minus 1 if I'm using left endpoints, or x sub I minus 1 plus x sub I over 2 if I'm using midpoints. So this form is generically the form for the area in all cases. The only place where they differ is right in here, what goes in here. So what the book has done is it's using x sub I star as a placeholder to give us maximum flexibility with this notation. Here, if you want to say I want to use right endpoints, then the x sub I star should be replaced with x sub I if you say I want to use right endpoints. If you say I want to use left endpoints, then replace x sub I star with x sub I minus 1. And if you say I want to use midpoints, replace x sub I star with x sub I minus 1 plus x sub I over 2. So the x sub I star is just there to give us flexibility. It represents either the left endpoint, the right endpoint, or the midpoint, depending on which one you've been told to use or which one you've decided to use. So yeah, it's a lot of notation. You got the x sub i's by themselves. Then you got x sub I bar, which is the midpoints. Then you have x sub I star, which is meant to be a generic either left endpoint, right endpoint, or left endpoint, right endpoint, or midpoint, depending on what you've been asked to use or what you've decided to use. In theory, the x sub I star can be any point. It does not have to be the left endpoint, the right endpoint, or the midpoint. It can be any point from the subinterval, any at all. You can randomly pick a point. And it doesn't have to be the same point for every subinterval. So I say x sub I star can be any point chosen from the ith subinterval for each choice of I. So for the first subinterval, I could use the right endpoint. For the second subinterval, I could use the midpoint. For the third subinterval, I could just randomly pick a point. We don't have to use, the same point for every subinterval, and we don't even have to use left, right, or mid, okay? In this book, that's what we're gonna do because that's what makes it easy to do by hand. So we're always gonna either do left, right, or middle, and we'll pretty much for most of the time, consistently use the same point from each subinterval. So to find the exact area now, finally, remember that n represents the number of rectangles. To find the exact area, I'm going to stuff in infinitely many rectangles. I'm going to put in rectangles of width, basically the same width as the width of a point. And so I do that in a limit by sending n to infinity. And so to find the exact area, we use infinitely many rectangles. The way we get infinity into the picture is through a limit. And so here would be the expression for the exact area. Now, I want you to be very careful. This part is the same as our approximation. We're approximating it with n rectangles, and then we're slowly, in the limit, making n larger and larger. Eventually, we squash in infinitely many rectangles. If this limit exists, we conclude that we've found the exact area. And we give that exact area, we give it a new symbol. This symbol, which I'll talk about next week some more, represents the exact area below f of x, above above the x-axis, and between the numbers a and b when f is a positive function. And we'll talk a lot more about this integral, next week and in the future. And this notation here represents an approximation. So we have the approximate area versus the exact area. To find the exact area, I take the approximate area where we're using n rectangles to do the approximation, and I make n larger and larger and larger and larger. And if the limit exists, then we found the exact area. So that's the theory of it. It's not difficult, but there's all this annoying notation. So I put all the formulas and notation on one slide, okay? And the more you can look at this, the better it'll get. The trick to notation is to work with it. The more you can work with the notation, the easier it gets. That's the trick, okay? So remember, typically x represents any variable, and x sub I, x with a subscript, usually represents a constant. So I have a toy example here. Suppose x sub I is 2i. You should think of this as like function notation. So then if I want to know what x sub 3 is, just replace the I with a 3 wherever the I occurs. So x sub 3 would be 2 times 3, or just 6. If x sub I is 2 times I, then x sub smiley face is 2 times smiley face. So now let's find the formulas. The formulas are not difficult. So the first formula to start with is the width of the subinterval. Since we're using equal length subintervals, the formula quite simply for delta x is b minus a over n. Now here's the important part. I don't want you to just read the math. I want you to interpret the formula. B minus a is the length of the interval. The interval goes from a to b. So I'm taking the length of the interval, b minus a, and I'm dividing it into n pieces, right? That makes good sense because I'm literally taking my interval and dividing it into n subintervals of equal length. How would I do that? Find the length of the interval to begin with and divide it into n equal pieces. So that's a starting point. Once we have delta x, we can literally find everything else. So here's the next formula. It says x sub I is a plus I delta x, I going from 0 to n. So this gives us the formula for the partition. Tells me what number, what's x sub 1 actually equal to. It tells me what's x sub 2 actually equal to. What's x sub n minus 1? What's x sub n? So let's make sense of the formula. Okay, so look, if I want to figure out x1, starting from the very left endpoint A, I would go one step of length delta x to get to x1. So literally here, x1, starting from A, is one delta x step away. So starting from A, if I add a length of delta x, that gets me to x1. How about x2? Starting from A, I'd have to add delta x once, and then I'd have to add delta x twice. x2 is literally, you can, just read the sentence. x2 is, starting from A, we're just going to add on 2 more steps of length delta x. And that's how they all are. x3 would be 3 steps of length delta x away from A. Starting from A, I would do add delta x once, add delta x twice, add delta x a third time. That gets me to x3. So the formula here makes good sense, and you should interpret it. Starting from A, add however many lengths of delta x you need to get to that particular x sub I, right? So remember, we know B and A, and we know N. So at this stage, we know everything. If I know B, I know A, and I know N, I can find delta X. If I can find delta X, I can find X sub I. And the function is given. So at this point, we know everything. Just to remind you, a generic ith subinterval looks like this. How is that helpful? It helps us identify the generic notation for the left endpoint and the right endpoint. And remember, the book introduced extra notation for the midpoint, x sub I bar, but the midpoint is just the average, just the left endpoint plus the right endpoint divided by 2. And our choices for what to use for quadrature, our x sub I star can either be use the left endpoint, the y value at the left endpoint for the height of the rectangle, use the y value at the right endpoint for the height of the rectangle, or use the y value at the midpoint for the height of the rectangle. And just in theory, x sub I star can be any point, And the exact area we find by taking the approximate area and then using more and more rectangles, sending n to infinity with a limit. Okay, so this slide, I wanted to put all the notation in one place for you. And we'll come back to this slide a little bit later. So one other comment I want to make before doing a quick example is, in this section, there are 2 types of problems we will be asked to do. And this is where a lot of the confusion happens for the students. So this part is important. The first type of problem we're asked to do is to approximate the area. We're not finding the exact area, we're just approximating it. In this case, n, the number of rectangles, will be a fixed positive integer that is usually given to us. And then quite simply, we use our formula. Let me remind you of the formula, how I want you to interpret this. So the first thing I realize is this is a sum. So I say, okay, this is going to be repeated addition. So now what are we adding? I've got height times width. Height times width is area. So this gives me the area of the ith subinterval. And now I'm adding all of the subrectangles to find an approximate area. And now for the height, how are we finding the height? Well, there's 3 different ways. If you say I want to use left endpoints, then I'm going to replace the x sub I star with x sub I minus 1. If we're told, oh no, you need to use the right endpoints, then I'm going to replace x sub I star here with x sub I. Then you say, okay, hold on, I changed my mind. Let's use the midpoint. I'm going to replace x sub I star with x sub I minus 1, where x sub I is given by the formula a plus I delta x, and delta x equals b minus a over n. And the big difference I want to highlight here, where n is a fixed positive constant. That's a big deal, okay? Because we compare this to the other type of problem that we will be asked to do. The other type of problem is not to approximate the area, but to find the exact area. In this case, not much changes except one thing. In this case, n is no longer a constant. N will be treated like a variable. And we will send n to infinity. In this case, n will not be given because it's just a variable. It's just the letter n. We use basically the same formula. When you look at this formula down here, I don't want you to get too confused. Start by looking at the sigma notation. First, start with the sigma notation. And here, I'm going to do it again. I know it's getting annoying, but that's what you paid me to, I want you to make sure you get this. So look at the sigma notation. Look at what the sigma notation is adding and start by saying, aha, height times width gives me area of the ith subrectangle. Now let me add them all up. This gives me the approximate area. And now finally, let me send n to infinity to find the exact area. Everything stays the same. The only difference is n is a variable. All the other formulas are the same. X sub I is still a plus I delta x, and delta x is b minus a over n, except here n is kept as a variable. As opposed to the previous case when in the approximation problem, n is kept as a constant in the previous case, in the approximation problem. So one other thing I forgot to mention is, okay, I have a formula for x sub I, that's great, but I never got a formula for x sub I minus 1. So the formula for x sub I will tell us the formula for x sub I minus 1. Remember, this notation, we should interpret it like a function notation. So here, if I replace this I with an I minus 1, then I need to replace this I right here with an I minus 1. So the formula for x sub I minus 1 is just a plus quantity I minus 1 times delta x. So I would just replace these i's with an I minus 1 to find the formula for x sub I minus 1. The formula for x sub smiley face is equal to a plus smiley face times delta x. And you know I hate to do that. So these are the two types of problems that we will be solving, and depending on whether you're approximating or finding the exact area, you will approach this slightly different. So let's do here an approximation problem. I'll do this quickly and stop. So this is approximate the area. So I'm not going to take a limit here. Here n will be fixed. In fact, they've told us n is 5. Use 5 subintervals. And so I also need to know for my rectangle, how am I going to approximate the height of the rectangle? So here they say, use the right endpoints. Okay, so let me slowly start this. We always start by calculating delta x. Delta x is just the length of the interval divided by n. Delta x is b minus a over n. Here the interval is given as 0 to 5. And n is given here as 5. That's the 5 subintervals. If we're finding the exact area, n would just be left as the letter n. Okay, well, I'll do an example like that next time. And so I found delta x. Once I find delta x, I can find x sub I. X sub I is just a plus I delta x. I know a is 0. And I know that delta x is 1. So a plus I delta x just looks like 0 plus I times 1, or x sub I just equals I, where I goes from 1 to 5. That's really important. Don't forget. Y5, that's the number of subintervals given to us here. Here, little n equals 5. So now I know how to make my partition. In this problem, it wasn't hard. If I asked you to divide 0 to 5 into 5 equal subintervals, obviously we would divide it at 1, 2, 3, 4, and 5. But if the numbers are more complicated, this method always works. So now I know x sub 1 is 1. I know x sub 2, so plug in a 2 everywhere there's an I, x sub 2 equals 2. X sub 3 is 3. And now I can go ahead and do the procedure. What's the procedure? Well, from the first subinterval, use the right endpoint, the y value at the right endpoint. So my area of my first subrectangle is going to be f of 1 times 1, where f is this function here, x squared. For the second subinterval, same concept. I'm going to go to the second subinterval, choose the right endpoint here. The y value at the right, so f of x sub 2, f of 2 will be the height times delta x, which is 1, and that'll give me the area. So here I did it in two ways. So here I did it using the notation. So here's the formula for the area. We want right endpoints. So I'm going to replace the x sub I with, I mean, the x sub I star with x sub I, because we want right endpoints, and the right endpoint is x sub I. And x sub I we calculated is equal to I. So here we calculated x sub I equals I. And so that's what I'm just plugging in right here. And then the function here, f of I, the function is x squared. So here, the function is the squaring function. So f of I is just I squared. And now you can either evaluate the sigma notation. Here, I noticed that it's one of our, it's a form that we have a shortcut formula for. So here I use the shortcut formula, but you don't have to. Actually, me personally, I would just do it this way, where I just calculate explicitly what the sum is, you know, because I don't necessarily have the formula at my fingertips. And I don't want to necessarily make it more complicated than it is. Yeah, I could use a formula, or I could just do the math. So I will continue with this example here. I will come back to this example, continue next time with this example. But you also please read ahead. As I said, the concept isn't difficult. At the end of the day, all we're doing is multiplying and adding. What's annoying is the notation. And practice makes perfect. The more you can look at the notation, the better it gets. All right, everybody, I'm going to stop right here.